This is an update to the ETE2801L Industrial Electronics Transformer Characteristics and Application Lab for spring 2020 during the COVID-19 virus time. So the initial discussion talks about the basic equations associated with the transformer, primary and secondary relationship, and the turns ratio, and the fact that a transformer is a pretty efficient device, so we generally assume power in and power out are the same. We'll confirm that in measurement. And then the turns ratio is the inverse of the voltage turns ratio, the current turns ratio. The basic transformer we're going to be using is this one right here. I give you the data page associated with this device. You can download and look at it. There's a website and then a data sheet to show you how things are connected. I also point you to another web page from a Denver University faculty member who does a great job on industrial power devices. The transformer itself, if you look at it closely, and we looked at it in class, we notice there's the metal parts and then the windings. If you took that apart, you'd see that the metal part is actually separated into two parts. We often call these the E and I core because it looks like an E and I core if you turn it on its side, right? And that's how the unit is put together. The bobbin, which holds the wire, sits inside of the transformer. Most of these manufacturers will wind the primaries as a common value because that voltage is usually known, and then the secondary winding is custom for the voltage that you want. So when we look on here, we see the primary, which is the finer winding, the higher voltage, and then the thicker wire is the output or the lower voltage. Lower voltage, higher current, higher voltage, lower current. More turns, less turns. So the first part of the laboratory is to basically measure the resistances to confirm what we have. So that's pretty straightforward to do. If we measure the primary, what we see is a amount of ohms of 50 ohms of resistance. If we look at the secondary winding, and we see it's even smaller, of course, and 2.2 ohms. So about a ratio of 25:1 on the resistance. If you measure around any of the other connections, so if I measure here, any place there, you'll have an open. So there is no winding connection. It's only the one winding at a time will have a connection. So within this picture where we see 4 windings, there's no connection between this winding and the other 3. So we measured those values, and then you'll record those and comment on them. Moving on to the active portion of the measurements, we'll be using 2 different circuits, mostly for instrumentation. When we're going to vary the input voltage with the variac, the unit we used in the AC Power Lab, we'll use a voltmeter on the bench to measure those voltages. When we have a fixed voltage, we know that the watts up meter works well with, or the kilowatt meter, sorry, works well with the fixed voltage, and so we'll be using this circuit in the latter part of the part 2 of the measurements. This of the active measurements, we're going to connect a voltmeter, adjust the variac, and then take measurements from basically just the full range of the winding voltages. This primary winding is rated 115. will go from 10 volts to a maximum value recording every 10 volts. So I'll record that data and then you're going to analyze it. So for the next part of the experiment, we're going to collect current data. As I've told you, my preference in taking current data is certainly to measure voltage across a resistor and then divide by the resistance to get the current, but that's not always possible to do. And so in some cases you must break the circuit. So that's what we're going to do in this part of the lab. We're going to take the wire from the variac, the black wire. We're going to pass it into the ammeter, and always selecting AC amps, in this case milliamps. We're going to come back from the meter using the blue wire to then go into the transformer via this yellow cable. And then the white wire will complete the circuit back to the white wire of the variac. On the output of the transformer, we're going to put a resistor. This resistor is a 10 ohm, 10 watt resistor. We're going to have enough voltage in this case and current to exceed 10 watts or come very close. So we will measure the voltage in this case across the voltmeter, or across the power resistor, the white resistor here. Then we'll divide by the resistance of the resistor, which I measured to be 11.5 ohms. The resistance will change a little bit with temperature, so it is not constant, but it's close enough in this example to get the current relationship. So we'll measure primary current on this meter. We'll measure secondary voltage, divide by the resistance value to get secondary current, and then you'll analyze that data. In part 3 of the laboratory, we're going to do the polarity tests and voltage regulation tests for the transformer. So since these are fixed voltage tests, we're not going to change any voltage for the transformer. We can switch over to using the kilowatt meter, which we used last week with the single phase power lab. And then we're going to just measure voltages and reconfigure. In the first circuit, we're going to adjust or set up for 115 volts to 20 volts with one primary and two secondaries. So in this case, one primary will be energized and two secondary windings will be put in series. Now remember, you must follow the dot polarity of the transformer. So in this case, we see a dot on 5 and a dot on 7, which means the dots are equivalent to a positive sign, if you will. And so I can connect 6, which does not have a dot, to 7, which does have a dot on the transformer winding, essentially putting those two voltages, 5, 6 and 7, 8, from the windings in series to give me my 20 volt output. All right, so we'll take that data and then we will make a measurement with the nominal voltage and then see the load regulation as the resistance is placed on the circuit. Again, we'll use the same resistor. On 20 volts, you need to take a little quicker measurement because 20 volts would, if left on that power resistor, would exceed the rating. But for a short time, it will be okay. So here's the first setting. The input voltage is 115 volts from the kilowatt unit. Of course, there is very little load on the transformer, so current is minimal, watts is minimal, volt amps is minimal, and so power factor is very low because it's just the inductor. The voltage out of the transformer is, in this case, 23.78 volts. That's what we call the open voltage, or the no load voltage, because we don't have the resistor connected. So I'm going to move the connection over to the resistor, and you will see the effect of loading the transformer. And you can see that we got a pretty big change, almost 7 volts by loading the transformer. So we're actually overloading a little bit, dropped to 16 volts there. 23 to 16 volts. And that's because the current that we were conducting was 23 over 11 ohms, which is 2 amps, which is close to the limit of the transformer. So transformers, although we treat them as ideal, they are affected by loading. Again, 23 volts, 23.7 volts, no load, 16.6 volts loaded. So here is the first test with the transformer. I have 115.2 volts to 0.3 volts on the input primary. On the secondary, I currently have I disconnected the load of the secondary voltage so that I can test the two windings in series. So here is the voltage on the secondary. It's 23.8 volts. That's open circuit. There is no connection. We would say no load, right? And then I'm going to connect the 20 ohm resistor, which will create the 1 amp output, which is the rating of the transformer. So you can see as soon as I apply a load, the voltage changes a little bit. It changed to 23.3 volts. Not so bad. 23.8 to 23.3. Now I had previously done this with a smaller valued resistor. Alright, so here is the input voltage, 115.3 volts RMS, and then the output voltage, no load, is 23.79. So now I'm going to connect the output secondary to a resistive load. So we'll keep an eye on the voltmeter when we do this. And you can see that the voltage under load drops to 19.3. So almost 4 volts have dropped on the transformer. Clearly, there's voltage loss in the transformer when it's under load. In this case, I have 2 of the 10 ohm resistors in series, and that makes for a full load on the transformer. So don't believe the transformer is just an ideal relationship with current and voltage. Okay, we'll move over to the next test. The next test is 3C, 115 volts to 20 volts, 2 primaries interconnected in parallel, 2 secondaries in series. So if you take a look at the back final sheet of the document, you can see how you connect circuits in parallel. In this case, 115 volts in parallel means we connect each of the respective primary windings, maintaining dot polarity, so 4 and 2 go to the same point, 3 and 1. On the output, same as before, we have the 20 volts, so we have 2 in series. So what we really want to look at in this circuit is how the voltage regulation changes. So The output voltage is very similar to previous. We have two windings now, but they're both 115 volts. Output voltage is 23.8 volts. Now previously we saw the voltage drop to 19 volts, so we'll see what happens now. And you can see that the voltage only dropped to 20 volts. It still dropped because of the loading of the resistor, but by using two windings instead of one, we're actually using the full capability of the transformer, and we get better voltage regulation. And that's why you should use all windings on the transformer when you activate it. Even if the output voltage is the same as previous, 20 some volts, 20 to 23, we get better performance if we have both of the primary windings in parallel. For the next circuit, 3D, we have 115 volts to 10 volts, two primaries interconnected in parallel, two secondaries in parallel. So we're going to have the lower voltage, but we're going to have all four windings, both primaries, both secondaries, active. Alright, so the input voltage is just a little over 115 volts. We'll adjust it a little bit to, there we go, 115.6 volts. It jumps a little bit. 115.1. And the output voltage is 11.8 or 0.9 open circuit. Now we're going to put on the load. And again, this will be a 10 ohm load. And we see that the voltage drops to 10.98 volts. So loaded, 10.98 volts. Unloaded, 11.9. So only a 1 volt drop in this case. So much better than the previous case we had with just one winding. For the final case, we're going to have 230 volts to 10 volts, two primaries in series, two secondaries in parallel. Actually, we're not going to go to 230 volts because the Variac cannot produce more than about 130 volts. So the numbers will be lower, but I think you'll understand the operation. So again, in series, we must follow dot polarity. So dot to no dot, and then dot to no dot is the input. On the output, the secondary is in parallel, and that is the same as the previous case. So this is part 3E, which is we'll have the maximum of the two windings in series, and we'll crank this up to maximum voltage, about 40 volts. That gives us about 7 volts output, which should be closer to 10, but we'll live with that. And we see 7 volts on the output unloaded, and now we will do the loading of the output and see how the voltage changes. So from 7.2 volts to 6.6 volts, only a change of 0.6 volts. So this is loaded voltage of 6.6 and unloaded 7.2. This test is not exactly as specified by the manufacturer in terms of 230 volts, but we got up to about 138.9 or almost 140 volts. Okay, the last part will be the testing associated with the grounded output. This part of the laboratory, part 4, is a very interesting section in terms of relating it to how your home works. Normally your home, we bring in with Southern California Edison, maybe 12,000 volts to the local transformer. The local transformer produces 120 and 240 volts. But they do it in an interesting way. We're only going to energize one winding here, but we could too. But you'll notice that what we're doing on the output is we have a series connection for the two output windings, but the middle winding is going to be grounded. Now what that does is that makes that point 0 volts. But on this side, because of dot polarity, this voltage is going to be increasing with respect to this point. And this end is going to be decreasing because there is no dot. Now because a transformer acts like a winding acts like a battery in space, there is no problem with connecting the two ends of a battery together. We're not connecting the full circuit together, we're just connecting the two ends. Now, the interesting part about this is between each winding from here to here is going to be our output voltage, in this case 10 volts and 10 volts, but between the two windings we get 20 volts. And this is exactly how you get 120 volts in your home and also 240 volts in your home. We like to use the higher voltage for the higher current loads or higher power loads, such as air conditioners, dryers, electric ranges. Now when we interconnect this to the scope, you're going to see two different voltages. These two voltages come from the channel 1 and channel 2 off of the secondary. This middle winding, we would sometimes call the center tap, is going to be grounded with the scope, and because it's the output of a transformer, there's no galvanic connection between input and output, we can ground that one lead, right? And then we will see that between the two voltages, we get the larger or twice the voltage in the system. So we'll set that up on the scope and display these waveforms. All right, so the setup has been made, and this is the scope display, very similar to what is in the handout. The green and yellow traces are the two ends of the transformer. In this case, the red wire here and the red wire there. The center tap is connected together via the yellow wire and then grounded to the scope ground. So that serves as the reference for channel 1 and channel 2, which are the red points. If I want to look at the difference between those two, or each end, I'm going to use, in this case, I use the math function, and the math function just allows me to do a subtraction of the two channels. So you can see my operator down here is subtract between channel 1 and 2. So plus minus a minus becomes a, looks like I got my channel switched up here, but plus value minus a minus becomes a double plus, and a minus a positive becomes a negative value. So in your home, the green and yellow are 120 volts, but between the two ends of the transformer is 240 volts. And that's how we get two different voltages in our home. Now you might think that on a transformer it'd just be as easy to ground one end of the output of the transformer and then use 115 and 230 volts. But in this case, we're using only the 230 volts for both windings. If we tried to do that in the AC case, the 115 volts would only use one winding. In this case, we get two low voltage circuits and one high voltage circuit. So that's the advantageous way to use this grounded transformer. This only works because the transformer is isolated on its outputs. If these were not isolated from the inputs, then I would not be able to ground this because I would have a reference and that would cause a problem. So you must be very careful when you make these kind of measurements on the scope. I could actually disconnect my ground connection and it would still work because the scope would have a reference through the through its input signal. But so you can always do channel 1 minus channel 2 in this case, and it will work fine, no grounding at all. Mark Bailey would always suggest that you don't ground the scope, but I grounded it just to show you that indeed it does work as designed. So that's the data that is collected from the transformer. I will send that data. I'll include that data in the handout. And that's the basically the end of the transformer laboratory. We're going to set it to 100 kilohertz and 2 volts peak.